So I didn't get a chance to give a lot of details about elliptic galaxies or the patterns of mass versus rotation in spiral galaxies. We'll get to some of that maybe later. But I want to tell you what we know about galactic evolution because it'll give us a framework for thinking about this in the same way that the history of the solar system gave us a framework for thinking of the solar system. Galaxies, it turns out, evolve in a very different way than stars. Stars, essentially, unless they're in a very close binary, evolve pretty much independently. A star evolves on its own evolutionary track. Galaxies are far more social creatures. Remember that most galaxies are found in clusters. Many stars are found in clusters. But in a cluster of galaxies, the fraction of the volume taken up by the galaxies is much larger. Remember that if you count the halos, Andromeda and the Milky Way essentially are touching. Even if you don't count the galaxies, compute the ratio of size to distance between, say, Andromeda and the Milky Way, and size to distance between, say, the Sun and Proxima Centauri, and you will get the idea that while interstellar space is vast and empty, intergalactic space is far less vast, especially in the context of a cluster. And so interactions between galaxies, therefore, are going to be far more important in the evolution of a single galaxy than is the case in stars. And now, I talked about spiral galaxies. We find, as part of our hints to understanding how galaxies evolve, that elliptical galaxies are far more common in the interior, in the center of the core of the densest clusters, in the areas where they're densest. And this is the region where you expect galactic interactions to occur more than anywhere else because the galaxies are packed tight near the center. And galactic interactions, it turns out, can destabilize the disk structure. This is sort of a reasonable thing. Imagine, remember, the disk maintains itself because of conservation of angular momentum. So you have a bunch of stars orbiting in one particular direction, but then they collide with another bunch of stars with a different direction of angular momentum. Those collisions will lead to a common angular momentum, but the flattened disk structure will probably not survive, and the result of collisions is likely to be, since you have collisions with, collisions of stars are gravitational collisions, they're scattering events, but the result will be that stars will go off in with varying orbital parameters, and the net result is sort of this elliptical galaxy where stars orbit with all kinds of inclinations. And so, if you believe that collisions and mergers happen in a cluster, you would expect ellipticals to survive in clusters, and that is indeed, in the centers of clusters, that is indeed what we find. There's another difference between galaxy clusters and star clusters, or galaxies as large clusters of stars, which is that in between stars, the interstellar medium is there, but the interstellar medium, remember, gas and dust, the whole interstellar medium in the Milky Way comprises a tiny fraction of the mass of the Milky Way, unless you count the extended halo, in which case maybe it counts for about half the mass of the Milky Way, excluding dark matter. In the case of galaxies, we find that this is very different. The typical galactic cluster is full of hot gas, where by hot, again, I mean million Kelvin gases, and the mass of this hot gas usually exceeds the sum of the masses of all of the galaxies. So a majority of the, again, excluding dark matter, a majority of the mass of a galactic cluster is actually spread out in between the galaxies in the form of intergalactic medium. And again, we think of interactions as the reason for this. In galactic interactions, tidal forces can strip a small fraction of a galaxy's gas away and eject it out into the interstellar medium. And then if we have recurring interactions, then over time, some significant quantity of gas will be transferred to the interstellar medium. The net result is the observation that in galactic clusters, most of the mass is in between the galaxies and not in the galaxies. So what do interactions between galaxies look like? Well, galaxies colliding is certainly not like cars colliding, because galaxies are sort of, for all that they are massive, they are extended objects, and the main interaction between two galaxies is gravitational. So the typical interaction at slow relative velocities is a very stately thing. It's a gravitational interaction. A typical case to study is sort of the motion of a dwarf galaxy through the plane of the Milky Way, or a globular cluster on its orbit through the plane of the Milky Way, or of a globular cluster from one galaxy through the plane of another galaxy. And it's a little bit tricky to make the calculation, but you can sort of imagine that if you have a bunch of stars scattered around, and then along comes a globular cluster pushing through, moving this way, then in its wake, what is going to happen is that the stars are going to be gravitationally attracted to this visitor, and so there will be a motion of stars towards it. And it takes a while for the stars to move, and after the cluster has passed, there will be a wake, a region of increased mass density from where it has attracted stars. So an object moving through a field of stars always is dragging behind it increased mass density, which is decelerating it. And it, in turn, is, of course, accelerating these stars. So momentum is being transferred from the moving object to the galaxy relative to the collection of stars relative to which it is moving. This is called dynamical friction. And because it's a second-order gravitational effect, it's not surprising that it increases like gm squared. Why gm squared? Because the first gm is the magnitude of the wake that the star creates, and the second gm is the magnitude of the force that wake exercises on the star. So 2 GMs, rho is the density of the medium. Of course, a denser medium exerts more friction. And then this 1 over v squared can be argued either from dimensional grounds, v being the speed with which this thing is moving relative to the stars around it, or because the basic idea is the faster you're moving through, the less time there is for this wake to establish itself and exert a force on you. The net result is that a visitor will be slowed down. So a globular cluster, as it passes through the disk and through the disk population, will be slowed down and slowly spiral into a smaller and smaller orbit. And eventually, its interactions with the disk will become so frequent that tidal forces will then break it up, and the globular cluster will not live forever. It'll eventually merge with the disk. And this will happen faster for massive clusters. So if you started with globular clusters with all kinds of masses, the smallest one would survive the longest. Another sort of observation to file away, this is what a slow collision between galaxies look like. There are faster collisions where the relative speeds are bigger, and essentially the two galaxies pass through each other without time for wakes to get organized, without the stars having time to react. V is much larger. The stars still rearrange each other, but they rearrange with a delay. This liberates gravitational energy that was converted while the galaxies were accelerating towards each other. Some of that is converted into kinetic energies of the stars. The result can be the expulsion, a large amount of kinetic energy of the stars in one galaxy. And in dramatic cases, like the something Cartwheel Nebula, like the Cartwheel Galaxy, this has caused the emission of a lot of gas in a circular ring around the galaxy, and the stars that we see here, these blue stars, of course, are nothing to do with, they were not ejected from the galaxy. The gas was ejected. The gas is plowing into the intergalactic medium. That's creating a high-density shockwave, and that's generating star creation. So this beautifully decorated ring around the galaxy is marking the place where the shockwave is progressing through the intergalactic medium, and this may well have resulted from a collision with one of these two objects here over on the right. Another case is this elliptical galaxy, which has what is called a polar ring, likely the result, similarly, of a collision. Perhaps the collider was destroyed and merged with the elliptical, but the resulting energy ejected this ring. Now, these rings are very useful because they do not orbit in the plane of a galaxy. They are influenced by the gravity of whatever is around there. This gives us an opportunity to measure, by studying their orbital parameters, the dark matter distribution perpendicular to the plane, and someone might have argued, based on the orbit of the sun and the stars and the clouds in the Milky Way, that dark matter could be confined to the disk of the Milky Way. The reason we are absolutely certain it's a spherical distribution is that the orbits of these objects, which orbit way outside the plane of the galaxy, agree with predictions of the cold dark matter model. When the collisions are more delicate, or in any collision between galaxies, remember galaxies are in free fall, the gravitational attraction or the gravitational interaction of one with the other is a tidal interaction, and this can lead to these beautiful objects. On the left, of course, M51, the Whirlpool galaxy, interacting with not quite a collision, but obviously an interaction with the smaller galaxy in the upper right. We see that one of the spiral arms has grown and is extending towards this galaxy, and slightly outside the frame, the other spiral arm extends very far to the left. These are both tidal effects. Gas or material in stars are being attracted on the one hand and attracted away from the galaxy on the other hand, in the same way that we get high tide on two sides of the Earth. These are the tidal effects of the passing galaxy, and an even more brilliant example of these sort of tidal tails are these antennae galaxies, as they are called here. Again, a pair of galaxies in collision, and we see the effects of tidal forces in these large tendrils of gas that have been emitted by both of the galaxies. In another recent observation of the same effects, NGC 6872 has recently been measured to be the largest spiral galaxy known. The scale here is 100,000 light years, so this thing is about 2 or 3 times the size of the Milky Way, but that's kind of cheating. One of the reasons these spiral arms are so extended is because it seems that this has undergone a collision, perhaps with this guy over here in the upper left, and so it's got these two tidally extended spiral arms coming out on two sides. And the most exciting thing here is that there is some structure in this upper left tidal tail, and it seems as though some of the tail has become sufficiently cold and dense to collapse, and there is the region that is encircled there is a region where astronomers suspect that a actual globular cluster or a dwarf galaxy might be forming. So this is the weird case where, rather than destroying galaxies and merging them, here a collision is actually creating a new galaxy, a new wrinkle on our theories of galaxy interactions, something modelers will indubitably incorporate as time goes on, if indeed this thing is verified. Now, an interesting question you might ask is, well, so if what you're telling me is that very often two galaxies will in fact merge because they will be slowed down, ripped apart by each other's tidal effects, and in fact end up as one merged object. Well, that's very nice for the stars. They can orbit whatever they want in the gas. Each of these galaxies would have had a supermassive black hole in its center. What do those do? Well, that's an interesting question. And what you would guess, of course, is that the two black holes, being so massive, would very rapidly find themselves in the core of the combined object. So you could find yourself in the interesting situation like NGC 6240, which is a galaxy whose shape clearly suggests a past in which some interaction happened, and an X-ray image of the center shows two X-ray sources, two black holes. This has a binary supermassive black hole, and they are separated by, this doesn't say, but what it meant to say is that these things are separated by on the order of 3,000 light years, or a kiloparsec, an eighth of the distance from the sun to the center of the galaxy is the distance between these two supermassive black holes. Those are some very interesting, highly relativistic orbital dynamics, and over time, of course, friction with the dynamical friction with the medium, as well as gravitational radiation, will cause these things to eventually, over hundreds of millions of years or billions of years, to spiral closer to each other, eventually merge, and there you'll get a blaze of gravitational radiation that perhaps someone will be able to detect at that point. So based on all these observations of galactic interactions, we could try to understand a model of galaxy formation. And the original model of galaxy formation was basically the solar nebula writ large. So remember, the solar nebula formed from a cloud that collapsed, protostar, that story. Imagine the same thing on a galactic scale. So this is the cartoon version of the ELS model of galaxy formation. You start with a protogalactic cloud. The protogalactic cloud collapses. In the center, where the density gets highest, stars start forming long before the densities on the outskirts are high enough. Eventually, of course, angular momentum will flatten the cloud just as it did the protostellar disk. But in the center, perhaps enough stars formed and clusters managed to collapse, so there was fragmentation, and smaller subclouds became critical and collapsed before the flattening. So then you'd find the old globular cluster stars orbiting in orbits that are not necessarily in the plane of the disk, and then eventually the disk flattens out and you get the issue of it, the shape of the galaxy as we know it. This is a very reasonable model, and it probably is part of the truth. There are some issues with it. One is it explains why you find halo stars and halo clusters orbiting in inclined orbits, but not why so many of them are in retrograde orbits, considering that as the cloud collapsed, angular momentum conservation would have sped up whatever rotation it has. It also turns out that this collapse occurs very rapidly, and it does not leave for a cloud the size of the Milky Way. This is the Kelvin-Helmholtz gravitational collapse timescale. It's a rapid timescale, and even in the case of a cloud the size of the Milky Way, you don't have 2 billion years in which to create halo stars. Remember, the ages of globular clusters were between 11 and 13 billion years. This is one of the key pieces of evidence that this model is not sufficient. In addition, there's this correlation between distance, orbital radius, and metallicity in globular clusters that says that the distant clusters are younger. This does not match. In this theory, you'd expect the clusters formed in the center to be the oldest ones, and also the fact that the disk components, the thin and thick disk, differ in age. In this model, everything happens fast, and you'd expect stellar creation to start in the disk as soon as densities got high enough, and there is not, again, billions of years of separation that can explain all of the phenomena that we see. So this is not a sufficient model. Another sort of opposing model is what's called the hierarchical merger model. In this case, a galaxy forms more the way we said planets form. So there is a collapse, and what collapses are basically globular clusters or dwarf galaxies, protogalactic fragments, and they can have a mass from 1 million solar masses to maybe bigger than a galaxy. But in the usual way that fragmentation works, we know that the most common will be the smallest ones. So you'll have a lot of globular cluster-sized protogalactic fragments with a mass of about 1 million solar masses. And then, as these orbit each other and interact with each other, dynamical friction slows them down, and eventually they are brought into this big spherical mass distribution, and their density becomes high enough that they start forming stars and globular clusters in the center. And because these things have formed stars individually, then in the center of each cloud you start star formation. Then this explains why you get different chemical histories, because different clusters independently initiated, different fragments independently initiated star formation. And then these things are now beginning star formation at the same time that they're interacting with each other. Collisions and tidal forces will break some of them. Which ones will break most likely? Well, the ones which experience the most dynamical friction, namely the most massive ones. So the more massive ones are more likely to be slowed down and disrupted because of dynamical friction. Those that have been disrupted will produce the halo field stars, and in some of the others, the stars and the gas will have been blown away, but the globular clusters, as more massive, will have survived, so we'll have bare globular clusters, and we'll still have some dwarf galaxies. In this model, about 90% of all the globular clusters formed, especially the massive ones, as I said, are going to be destroyed. The globular clusters we see in the halo today will be the 10% that survived, and with an emphasis on the less massive ones, which is why we typically find globular clusters with masses up to 1 million solar masses. And then, very early in the dense center, as these things are starting to merge, you form a bulge. So in this case, star formation proceeds from the inside out in this hierarchical merger model. And so you'd expect very old stars in the bulge. Explaining why there's new stars in the bulge is a detail of the model that I won't have time to get into. Of course, in principle, both models probably have a role to play. We do not have, I should say, a satisfactory theory of galaxy formation. This is an area of active research, but I think the consensus is that the hierarchical merger model, in a slightly more elaborate version than what I've described, is more likely to be closer to what it is that really goes on. Can we see any evidence of this? So for stars, we used clusters to test our theories of stellar evolution. How do you test your theories of galactic evolution? We do not have a long main sequence understanding, so we can't time galaxies in the way we timed stars, but we can look for very young galaxies. Where would you find very young galaxies? You'd find very young galaxies by looking very, very far. So this is the very famous Hubble extreme dark field image. Basically, the Hubble telescope was aimed at a region in the constellation Formax. This shows just a region 3 by 3 arc minutes in the sky, which, as far as anyone knew when they aimed at it, was completely empty of anything. There was no known objects in that region. And then they took a very long exposure, and in this field they found about 10,000 formerly unknown galaxies. They looked at a region where there was nothing in order to be able to focus on very dim and therefore very distant objects. These galaxies are billions of light years away. Aha. Billions of light years away tells us that we are seeing them billions of years ago. We'll get into that soon. And this means that the galaxies we see here are likely to be younger than the ones we see 1 million light years away, like Andromeda, or the Milky Way, which we see right now. And so, in this Hubble deep field, indeed we see that the galaxies seem to be bluer than the galaxies we see around us, and their shapes are far more irregular. It is a possibility that's under study that what we're seeing here is, in some of these cases, the proto-galactic fragments that will eventually form the galaxies that we see today. As I said, galaxy formation is still a very active field of study, and what understanding we have of the dynamics at the qualitative level we can handle, I think is all we're going to be able to achieve today.